Hey everyone, welcome to this news story. Today, we turn our eyes to the moon and the surprising wealth it might create far beyond Earth. On its surface lies a world of resources, craters, and hidden treasures that could change the way humans see money. For decades, people looked up and thought of the moon as empty and silent. But beneath its gray dust, there are rare metals, water ice, and energy sources that could be worth billions. Companies are already planning missions, building machines, and racing to stake their claims. What exactly is waiting there? How will this small, cold rock create fortunes larger than anything on Earth? And why is this new frontier so different from the land we walk on every day? In this video, we explore the moon's untapped riches and reveal how this tiny world could launch a new generation of billionaires. The moon is a natural satellite that orbits the Earth at an average distance of 384,400 kilometers. Its diameter measures roughly 3,474 kilometers, making it about 1/4 the size of Earth. The mass of the moon is about 1/80th of Earth's, and its gravitational pull is approximately 1/6 that of Earth. This reduced gravity shapes nearly every aspect of the lunar environment, from the way dust settles to the behavior of objects moving across its surface. The moon completes a rotation on its axis in the same amount of time it takes to orbit Earth, producing a phenomenon known as tidal locking. This synchronization ensures that one hemisphere of the moon constantly faces Earth while the opposite side remains hidden. The lunar orbit is slightly elliptical, causing small variations in distance from the Earth, but the overall pattern remains stable over long periods. The surface of the moon is covered by a layer of fine, powdery soil known as regolith. This material is the product of billions of years of meteoroid impacts and the slow breakdown of surface rock. Across the lunar surface, craters of all sizes punctuate the landscape, ranging from small depressions that measure a few meters across to massive basins spanning hundreds of kilometers. Some of these features formed billions of years ago, while others continue to develop from impacts that occur even in the present day. Alongside craters, plains known as maria appear as darker regions, composed primarily of basalt from ancient volcanic flows. These formations provide evidence that the moon experienced volcanic activity early in its history, although this activity ceased long ago. Beyond the surface details, the moon presents a complex pattern of resources that are of increasing interest for human exploration and industrial development. While historically it was regarded as a barren, lifeless rock, modern scientific analysis has revealed concentrations of metals and elements that could be of high economic value. Titanium and aluminum are present in the lunar soil, often in combination with oxygen, forming compounds that can be extracted and used for construction or industrial processes. Iron is also abundant, mixed with regolith in forms that can be separated and refined. Smaller quantities of rare elements, such as yttrium, scandium, and rare earth metals exist in specific regions, and these may be particularly valuable for advanced technology applications. The distribution of these elements is uneven, with certain regions showing higher concentrations due to geological processes that occurred over billions of years. In addition to metals, the moon contains volatile compounds that are crucial for future industrial activity. Water ice has been detected in permanently shadowed craters near the lunar poles. This ice exists in temperatures far below the freezing point of water on Earth, preserved in darkness where sunlight never reaches. The presence of hydrogen, oxygen, and other volatiles provides the potential for producing rocket fuel directly on the moon. By splitting water into hydrogen and oxygen, chemical propellants could be created, reducing the need to launch fuel from Earth. These resources also hold the potential to support life support systems, providing drinking water or breathable oxygen for humans operating in lunar habitats. The moon's lack of atmosphere and weather processes contributes to the preservation of surface materials. Without wind or rain, rocks, minerals, and ice deposits, remain largely undisturbed over millions of years. This stability allows for precise mapping and predictable extraction operations. However, the same absence of atmospheric protection also exposes the surface to cosmic radiation and solar wind, affecting both equipment and human activity. The regolith itself contains particles that are sharp and abrasive, capable of damaging machinery over time. Any industrial operation on the moon must account for these environmental factors to ensure the long term functioning of equipment and the safety of human operators. The temperature extremes on the moon are significant. During the lunar day, sunlight can raise surface temperatures above 120 degrees Celsius, while at night, temperatures can drop below minus 170 degrees Celsius. These variations influence the choice of locations for industrial operations. Polar regions experience more moderate temperatures and near continuous sunlight at certain peaks, making them ideal for solar power generation and habitat placement. By contrast, equatorial regions experience long periods of darkness and high thermal stress, which would require more robust thermal management systems for any machinery or structures. Understanding the moon's orbital dynamics is also essential for planning industrial activity. The predictable motion of the moon allows for the calculation of optimal launch windows and orbital transfers. Transporting materials from the lunar surface to Earth orbit or beyond requires precise energy calculations, but the lower gravity of the moon makes these maneuvers less demanding than Earth-based launches. The combination of resource abundance and relatively low energy requirements for transport underlies the potential economic value of lunar operations. Scientific exploration over the past decades has established a detailed understanding of the moon's geology and composition. Remote sensing from orbiters, sample return missions, and robotic landers have provided high-resolution data on mineral distribution, topography, and surface properties. Instruments such as spectrometers, radar systems, and laser altimeters have mapped the moon with increasing precision. These studies reveal patterns of high and low element concentrations, locations of potential ice deposits, and the topography necessary for constructing bases or mining sites. The knowledge gained from these missions forms the foundation for planning industrial activities and assessing the moon's potential to generate wealth. Economic analysis of lunar resources indicates that certain metals and volatiles have values far exceeding typical terrestrial deposits. Elements that are rare or difficult to extract on Earth can be mined more efficiently on the moon due to lower gravity and lack of interference from water or atmosphere. Helium-3, a rare isotope present in small quantities in the lunar regolith, has been proposed as a fuel for future fusion reactors, though extraction and transport would require significant technological advances. Even traditional metals, when combined with the strategic advantages of lunar-based production, could support new industries and generate substantial revenue. The moon's proximity to Earth also plays a role in its economic potential. At roughly 1 light second away, it is close enough to transport resources quickly, while being far enough to require its own self-sustaining operations. The combination of resource availability, accessibility, and relative safety makes the moon an ideal starting point for space-based industry. Its stable surface conditions, predictable orbits, and scientific knowledge accumulated over decades contribute to an environment where careful planning and technological investment could result in highly profitable outcomes. The moon presents both opportunities and constraints that will shape the creation of wealth. Industrial operations must account for gravity, radiation, temperature extremes, and the abrasive nature of regolith. Resource extraction, power generation, and transportation require careful engineering and detailed knowledge of lunar geology and orbital mechanics. Despite these challenges, the scientific consensus is clear. The moon contains materials and conditions that, if managed properly, can support large-scale economic activity. The combination of metal deposits, Volatile compounds, stable terrain, and proximity to Earth positions the moon as a location where industrial operations could generate wealth far surpassing most terrestrial ventures. Even in the earliest planning stages, the moon's potential for economic development was recognized. Proposals for mining metals, producing fuel, and supporting human habitats have been studied in detail. Engineering models and simulations demonstrate that with appropriate infrastructure, autonomous machinery, and robotic support, the extraction of resources could be continuous and scalable. By integrating solar power, in situ materials, and orbital transportation networks, operations could become self sustaining over long periods. The moon, in this sense, functions not only as a satellite, but as a platform for industrial expansion and technological innovation. The combination of physical properties, known resources, and accessibility forms the foundation for the argument that the moon could produce more wealth than comparable ventures on Earth. Each element present in the regolith, every crater containing ice, and every area of stable terrain contributes to the overall potential. Calculations based on current data suggest that with strategic development, lunar operations could support multiple industries simultaneously, from metal refining to fuel production. The predictable environment and reduced gravitational requirements lower costs compared to Earth based operations, further increasing the potential for profit. Historical lunar exploration has provided the first practical insights into these conditions. The Apollo missions, along with subsequent robotic explorers, collected samples, conducted surface measurements, and tested equipment under lunar conditions. These missions revealed the properties of regolith, the distribution of rocks, and the mechanical behavior of materials in low gravity. Later orbiters mapped polar ice and surface topography, confirming the presence of previously hypothesized resources. This cumulative knowledge forms the basis for current planning and supports the assertion that the moon is a viable frontier for resource based wealth creation. The moon's gravitational characteristics allow for different construction and extraction methods than those used on Earth. Machines can lift heavier loads with less energy, excavation can proceed with reduced mechanical stress, and transport between sites requires less force. These factors, combined with the abundance of materials, create conditions in which industry can operate efficiently. Additionally, the lack of atmosphere eliminates corrosion caused by air and water, which further enhances the longevity of machinery and infrastructure. Overall, the moon represents a combination of accessible resources, manageable environmental challenges, and logistical advantages. Metals, volatiles, and other elements exist in quantities sufficient to support industrial activity at scale. Engineering studies demonstrate the feasibility of establishing operational bases, extracting materials, and transporting products to Earth orbit. The predictable motion, stable surface, and detailed scientific understanding make the moon not only a subject of exploration, but also a location with the potential to support economic activity that could surpass conventional terrestrial industries. The moon's surface is covered by a layer of fine dust and broken rock called regolith. This layer varies in thickness across different regions, ranging from a few meters in some highland areas to more than 10 meters in certain basins. The regolith is composed of small fragments of rock, mineral grains, and glassy particles formed by repeated meteoroid impacts over billions of years. Each collision shatters existing rocks and melts portions of the surface, creating a mixture of coarse and fine material. Beneath the regolith lies bedrock, which is largely unbroken but may include fractures from tectonic activity and large impacts. The bedrock often contains layers of ancient lava flows or volcanic deposits that record the moon's geological history. Rocks on the moon fall into several primary types. Basalts are common in the Maria, forming from cooled lava that erupted early in lunar history. These basalts are rich in iron and magnesium and contain small amounts of titanium. Anorthosite is the dominant rock in the highlands, composed mainly of calcium-rich feldspar. Breccias are formed from fragments of rock fused together by impacts and are present in both Maria and highland regions. The composition of these rocks varies, reflecting the moon's long and complex geological past. The mixture of rock types influences the mineral content of the overlying regolith and the distribution of resources across the surface. Metal concentrations in the lunar regolith are of particular interest for industrial purposes. Titanium occurs in the form of ilmenite, an iron titanium oxide, and is concentrated in some Maria regions. Aluminum is abundant in the anorthositic highlands and can be extracted for construction or industrial processes. Iron is present in both ilmenite and other silicate minerals, and its presence contributes to the regolith's magnetic properties. Smaller amounts of magnesium, calcium, and manganese are distributed throughout the surface. Rare earth elements, including yttrium and europium, exist in trace amounts and are unevenly distributed. These elements are important for electronics, advanced materials, and certain chemical applications. Understanding their concentration and accessibility is essential for evaluating the economic potential of the moon. The moon's mineral composition is not uniform. Variations occur due to ancient volcanic activity, the size and frequency of impacts, and the movement of lava flows. Some regions show higher concentrations of titanium or rare elements, while others contain larger amounts of iron or aluminum. Detailed mapping of these variations has been made possible through orbital satellites and robotic landers. Instruments aboard orbiters measure the reflectance of the surface in different wavelengths of light, allowing scientists to identify mineral types in approximate abundances. Spectrometers detect specific wavelengths absorbed or emitted by minerals, providing a chemical fingerprint for each area. These measurements are complemented by high-resolution cameras and laser altimeters that reveal the texture and depth of regolith layers. Lander missions have provided direct evidence of mineral composition. Samples returned by astronauts contain rock fragments and regolith that can be analyzed in laboratories on Earth. These studies reveal the precise amounts of metals and other elements present in the samples. For example, Apollo mission samples confirmed the presence of ilmenite, anorthosite, and basalt in the expected regions. The particle size, shape, and chemical composition of regolith samples provide information about its formation processes and the distribution of materials on the surface. Future robotic and crewed missions continue to refine this knowledge, offering more detailed maps and higher resolution data for potential mining sites. Regolith contains both fine dust and coarser fragments, with particle sizes ranging from micrometers to centimeters. The finer particles are glassy and angular, a result of high-energy impacts that melt rock and cool rapidly. Coarser fragments retain the mineral structure of the original rocks and provide access to concentrated metal deposits. The mixing of fine and coarse material occurs over time as micrometeorite impacts churn the surface in a process called gardening. This continual turnover helps expose deeper material to the surface, making resource extraction feasible. Titanium-rich ilmenite is of particular interest because it contains both titanium and iron and can be used as a source of oxygen. By heating ilmenite in a chemical process, oxygen can be released for life support or fuel production, while the remaining metals can be processed for industrial use. Aluminum extracted from feldspar in anorthosite can be used for construction, both in lunar bases and potentially for structures in orbit. Iron and magnesium contribute to alloys and other materials essential for large-scale industrial projects. The combination of metals and volatiles makes the lunar surface uniquely valuable compared to most terrestrial mining sites. Remote sensing has improved with each new mission. Orbiters equipped with multispectral and hyperspectral cameras allow identification of minerals by their unique signatures in reflected sunlight. Regions of high titanium concentration, for example, appear differently in specific wavelength bands than areas dominated by anorthosite or basalt. Radar instruments can penetrate the regolith to reveal subsurface structures and layers, providing insight into the thickness of the dust layer and the location of bedrock. Neutron spectrometers detect hydrogen in the soil, offering information on potential water ice or hydrated minerals. These technologies combine to create a detailed map of both surface and near surface resources. The moon's surface minerals also show signs of space weathering. Solar wind implantation and micrometeorite impacts alter the outer layers of soil particles, creating nanophase iron and glassy coatings. These changes affect the reflectance and color of the surface, which scientists account for when analyzing spectral data. Understanding the degree of weathering is important for evaluating the quality of extracted materials. Some minerals retain their original properties, while others require processing to separate usable metals from the glassy matrix. In some areas, particularly in the lunar maria, basalts are enriched with iron and titanium. These regions are therefore primary targets for industrial activity. Highlands, while less rich in titanium, provide large quantities of aluminum and other silicate minerals. By combining information from orbital mapping and in situ measurements, it is possible to plan mining operations that access multiple types of resources in a single area. The distribution of metals is not random. It reflects the moon's volcanic history, impact cratering, and slow geological changes over billions of years. As technology advances, robotic systems and autonomous machinery will allow more precise and efficient extraction of lunar minerals. By analyzing spectral data in real time, machines can adjust excavation strategies, focusing on high value areas while avoiding low yield regions. This integration of observation and extraction maximizes the efficiency of operations. The combination of surface mapping, sample analysis, and predictive modeling forms a comprehensive understanding of the moon's mineral wealth, supporting long term planning for industrial and economic development. Water and volatile compounds exist in select regions of the moon, primarily near the poles where sunlight rarely reaches. These areas include deep craters that remain in permanent shadow. Temperatures in these craters can drop below minus 170 degrees Celsius, cold enough to preserve water ice over billions of years. The ice is not in large lakes or flowing bodies, but rather in small deposits as mixed with soil and rock. Layers of ice form thin sheets along crater walls and floors, often in combination with other volatile materials such as hydrogen, methane, ammonia, and carbon dioxide. The concentration of water varies depending on the location, slope, and the amount of sunlight exposure, with some craters holding more substantial accumulations than others. Detection of water ice and volatiles relies on remote sensing techniques and in situ measurements. Radar instruments on orbiting spacecraft can distinguish ice from surrounding rock by sending radio waves and analyzing the reflected signals. Ice reflects these waves differently than soil or rock, allowing scientists to identify its presence and approximate thickness. Neutron spectroscopy is another method that detects hydrogen, a key component of water. By measuring the neutrons released from the surface when cosmic rays strike, these instruments infer the presence and amount of hydrogen, which indicates potential water content. Infrared imaging can also detect ice by analyzing how sunlight reflects off the surface at specific wavelengths. Together, these methods provide a detailed map of ice-rich areas and support planning for future exploration. The distribution of water ice is uneven. Some craters at the lunar South Pole show significant concentrations, while many other shadowed regions contain only trace amounts. The morphology of the crater, its depth, and the surrounding topography influence how well ice can accumulate. Craters with steep walls and minimal sunlight penetration maintain lower temperatures, preserving more volatile materials. Shallow or partially illuminated craters may lose ice over time due to sublimation, where solid ice turns directly into gas under very low pressure conditions. Understanding these differences is critical for selecting sites for potential fuel extraction or human activity. Volatile compounds on the moon are essential for supporting future operations. Water can be separated into hydrogen and oxygen through electrolysis. Hydrogen serves as a propellant component, while oxygen can be used for breathing or as a fuel oxidizer. Other volatiles, including carbon dioxide, ammonia, and methane, can be utilized for chemical processes, creating additional materials for industrial or life support applications. The ability to produce fuel and air from local resources reduces the need to transport supplies from Earth, significantly lowering costs and increasing the feasibility of sustained operations. Ice deposits in permanently shadowed regions are often found mixed with regolith. The regolith surrounding these deposits contains small grains and rock fragments that can be processed alongside the ice. Techniques for extraction involve heating the soil to release water vapor, which is then collected and condensed. Heating may occur through solar concentrators, electric resistive elements, or other methods adapted to the extreme cold and low pressure of the lunar environment. This in situ resource utilization allows for both water recovery and the simultaneous extraction of other volatiles embedded in the soil. Polar regions present additional advantages for water harvesting. Peaks near the lunar South Pole receive nearly continuous sunlight, providing power for extraction systems. Adjacent shadowed craters contain preserved ice. By placing solar panels on sunlit peaks and linking them to collection systems in nearby craters, continuous operation is possible. This combination of permanent ice deposits and reliable solar energy creates a unique environment where industrial operations can function effectively despite the harsh conditions. The volume of water in some shadowed craters is substantial enough to support not only fuel production but also life support for human habitation. Estimates suggest that a few cubic meters of ice extracted each month could provide sufficient oxygen and hydrogen for small crews and limited propulsion systems. Scaling up operations could eventually provide fuel for spacecraft traveling to Mars or other destinations in the solar system. Understanding the exact distribution and accessibility of ice is therefore a key element in planning long-term lunar industry. Remote sensing continues to refine knowledge of lunar volatiles. High-resolution radar data reveals the depth and layering of ice deposits. Neutron spectrometer measurements quantify hydrogen content with increasing precision. Infrared and thermal imaging track surface temperature fluctuations, helping predict which deposits remain stable over time. These observations guide the design of extraction technologies and inform the selection of landing sites for future robotic or crewed missions. The combination of orbital data and sample analysis provides a comprehensive picture of the moon's volatile resources. Water ice is not the only volatile present. Hydrogen, captured from the solar wind, forms a thin layer in some soil particles. Other molecules, including carbon monoxide, ammonia, and sulfur compounds, are trapped in cold traps over geological timescales. These volatiles can be separated through chemical processes, offering additional materials for fuel production, industrial reactions, or environmental support systems. Each type of volatile requires specific methods of extraction and handling, adapted to low temperatures and low atmospheric pressure. In situ utilization of volatiles reduces dependence on Earth-supplied materials. Instead of launching water, hydrogen, or oxygen from the planet's surface, extraction directly on the moon can sustain operations with less cost and greater efficiency. Electrolysis of water, chemical conversion of other volatiles, and storage in cryogenic tanks are methods being studied for continuous operation. The combination of local resources, accessible energy, and robotic support forms the foundation for future lunar industry. Some craters contain layers of ice mixed with fine soil, forming a soft deposit that can be dug and processed. Other deposits are harder, more compact, and require mechanical breaking or heating to release water vapor. The texture and density of the ice containing regolith affect the design of extraction machinery. Techniques must balance efficiency with minimal disturbance to preserve surrounding material for ongoing operations. Understanding the physical properties of these deposits is therefore critical for engineering successful collection systems. The chemical composition of volatiles also affects potential use. Water is primarily AH2O, while hydrogen rich compounds may include trapped solar wind elements. Carbon dioxide and methane can provide fuel or raw materials for chemical reactions. Ammonia offers nitrogen for life support or industrial processes. By cataloging the types and amounts of these compounds, planners can determine which deposits are most valuable for long term operations. Resource mapping ensures that extraction occurs where it will provide the greatest benefit with the least effort. Ice deposits may also act as a protective resource. Because they are located in shadowed craters, they are shielded from direct solar radiation, reducing the effects of sublimation and preserving the material over long periods. Some ice layers may be meters thick, while others form thin films on the regolith surface. Combined with knowledge of surface topography, this information allows for careful planning of collection routes and storage areas, ensuring maximum efficiency and minimal loss. Exploration missions continue to refine understanding of these volatile resources. Instruments on orbiters and landers provide detailed measurements of temperature, composition, and distribution. These data allow engineers to model extraction processes, estimate yields, and plan for future expansion. The moon's polar ice and volatiles are therefore not static. They are part of a dynamic system shaped by sunlight exposure, regolith mixing, and occasional micrometeorite impacts. Scientific observation ensures that operations can be designed to respond to changes in local conditions over time. The combination of water ice, hydrogen, oxygen, and other volatiles forms the basis for sustainable lunar operations. By harvesting these materials, industrial activity can produce fuel, support life, and create chemical products without dependence on Earth. The integration of resource mapping, extraction, technology, and solar energy supply forms a complete system that is both efficient and feasible under lunar conditions. Each crater, deposit, and layer contributes to the potential for industry, establishing the moon as a location where resources can be converted into practical applications for exploration and economic activity. Long-term planning emphasizes not only extraction, but also storage and transportation. Collected water and volatiles may be frozen and insulated, transported to processing facilities, or converted into chemical propellants for rockets. The proximity of polar peaks with continuous sunlight simplifies energy supply for these operations. The layout of extraction sites and processing facilities can be optimized based on data from radar, neutron, and infrared observations. Each step, from identification to collection, is grounded in scientific measurement and engineering design, ensuring predictable and controlled operations. The moon's ice and volatile deposits represent one of the most significant resources for future industrial activity. By combining orbital observation, surface analysis, and technology for extraction and processing, it is possible to use these materials to support energy production, human habitation, and propulsion systems. The careful study of distribution, concentration, and chemical composition ensures that operations are feasible and productive. The preservation of these resources over geological time makes the moon a stable and reliable site for future industry. The potential of lunar volatiles extends beyond water. Hydrogen, carbon compounds, nitrogen-containing molecules, and trace gases provide raw materials for chemical reactions and fuel production. Extraction methods must adapt to extreme temperatures, low pressure, and abrasive regolith. With proper planning, These compounds can be harvested in a continuous, controlled manner, supporting both local use and transport to orbital facilities. The moon's volatile resources thus form a cornerstone of future industrial and economic activity, offering practical materials that can sustain operations on the surface and beyond. The moon experiences a day night cycle that is very different from Earth. A single lunar day, measured from one sunrise to the next at a specific location, lasts approximately 29.5 Earth days. This cycle produces long periods of daylight, followed by equally long periods of darkness. At the equator, sunlight falls directly on the surface for about 14 Earth days, followed by roughly 14 days of night. Temperature swings during these periods are extreme, reaching over 120 degrees Celsius in the daytime and dropping below minus 170 degrees Celsius at night. The angle of sunlight also varies due to the moon's slight axial tilt, which is only about 1.5 degrees relative to its orbit. This means that sunlight strikes polar regions at very low angles, creating areas of near constant illumination on elevated terrain, while adjacent craters remain in permanent shadow. The poles of the moon provide a unique opportunity for solar energy generation. Elevated peaks near the lunar south and north poles receive sunlight for nearly all of the lunar year. These regions, sometimes called peaks of eternal light, offer a steady and predictable source of solar energy. Solar arrays placed on these peaks can operate almost continuously, with only occasional interruptions caused by small dips in the horizon or by local topography. In contrast, equatorial regions experience long stretches of darkness, making energy storage essential for continuous operations. The combination of near continuous sunlight and stable terrain at the poles reduces the complexity of energy systems and enhances reliability. Solar energy on the moon has advantages over similar systems on Earth. The absence of an atmosphere allows sunlight to reach the surface without scattering or absorption. This direct exposure increases the intensity of solar radiation by about 40% compared to Earth at the same distance from the sun. There are no clouds to block sunlight, no dust storms, and no weather events that can disrupt energy collection. As a result, properly positioned solar arrays can produce energy at a nearly constant rate with predictable output over time. This stability is valuable for industrial operations that require continuous power, including mining, processing of regolith, and operation of machinery in remote locations. Designing solar arrays for the lunar environment requires consideration of temperature extremes and surface conditions. Panels must withstand long periods of direct sunlight followed by extremely cold darkness in areas where day-night cycles occur. Materials with low thermal expansion and resistance to radiation damage are preferred. Dust accumulation from regolith particles can reduce efficiency, so arrays may be equipped with cleaning mechanisms or protective coatings. In polar regions with near continuous sunlight, these design challenges are reduced, but the arrays still require careful engineering to maintain performance over years of operation. Energy storage is an important factor in lunar solar power. While polar peaks receive nearly constant sunlight, nearby areas may experience shadow or reduced illumination. Batteries, flywheels, or regenerative fuel cells can store excess energy during peak production and release it during short periods of darkness. In equatorial regions, where sunlight is present only half of the lunar month, storage systems must bridge the long nights to ensure continuous operation. Advanced storage methods are essential for supporting human habitats, industrial machinery, and processing facilities in locations that do not have continuous illumination. The combination of solar power and local resources enables in situ energy production. Solar panels can be deployed near mining sites, water ice deposits, or processing facilities, providing power without dependence on Earth-based supply lines. Energy can be used directly to operate machinery, heat materials, or produce chemical products. For example, electrolysis of water extracted from ice requires significant energy input, which can be supplied by nearby solar arrays. Similarly, heating regolith for extraction of metals or oxygen benefits from the continuous availability of local solar power. By generating energy on the moon, operations become self sufficient and scalable, reducing the cost and complexity of transporting fuel from Earth. The intensity of sunlight on the moon's surface is influenced by latitude, local slope, and surrounding topography. Crater walls and hills can cast shadows that reduce energy availability in some areas, while flat plains or elevated peaks receive more consistent illumination. Mapping sunlight angles with high resolution orbital imagery allows planners to position solar arrays for maximum efficiency. Seasonal variations are minimal due to the moon's low axial tilt, but small change in solar angle over months can slightly affect output. Detailed models of sunlight exposure are therefore essential for the design of energy systems that support industrial and habitat operations. The moon's lack of atmosphere also eliminates losses caused by cloud cover, air absorption, or scattering of light. On Earth, sunlight reaching the surface is reduced by approximately 30% due to these factors. On the moon, the full intensity of solar radiation reaches the panels, improving energy yield. Radiation from the sun is consistent and predictable, allowing long-term planning for industrial processes. This advantage contributes to the economic feasibility of large-scale solar-powered operations, including mining, manufacturing, and life support systems. Remote sensing has been used to identify optimal sites for solar energy collection. Orbital instruments measure sunlight angles, surface, slope, and shadow patterns over time. Data from these instruments indicate which peaks near the poles have the longest continuous illumination. Radar and imaging systems help assess surface roughness, which affects the ease of deploying panels and the stability of mounts. By combining sunlight mapping with surface analysis, engineers can select sites that maximize energy output while minimizing construction challenges. Large-scale solar arrays on the moon may differ from those on Earth in design and operation. Arrays can be modular, allowing expansion as industrial activity grows. Some concepts involve robotic deployment, where machines carry, position, and align panels autonomously. Other designs include flexible or lightweight materials that can conform to uneven terrain. Cooling systems are simpler than on Earth, as there is no atmosphere to conduct heat away, but radiative heat loss into space must be considered. Dust mitigation remains a key concern, as fine regolith particles can settle on panels and reduce efficiency over time. Solar power provides the energy foundation for lunar industrial activity. Mining operations, regolith processing, water extraction, and fuel production all require continuous power. Electrical energy can be converted to heat for chemical reactions, mechanical energy for machinery, or stored in batteries or fuel cells. By situating energy systems near resource-rich sites, efficiency is maximized, and transport of power over long distances is minimized. The combination of high sunlight intensity, predictable cycles, and reduced environmental interference makes the moon an ideal location for large-scale solar energy systems. The moon's long daylight periods in equatorial regions present challenges for storage, but allow significant energy generation during the day. Systems must store enough power to bridge the long nights. In contrast, polar regions with nearly continuous sunlight reduce the need for storage, allowing energy to be used directly for industrial processes. These differences influence the placement of facilities, selection of solar technology, and design of operational systems. Efficient energy management is essential for maintaining continuous operation of machinery, habitats, and chemical processes. Solar energy also enables production of propellants. Electrolysis of water from ice deposits requires large amounts of electricity. By providing power locally, solar arrays allow the conversion of water into hydrogen and oxygen, which can then be stored as fuel or used for life support. Similarly, regolith processing for metals or oxygen extraction can rely on solar generated energy. In this way, solar power links directly to the moon's economic potential, providing both energy and a means to produce valuable resources without dependence on Earth. Energy availability from the moon supports long term industrial planning. With predictable sunlight, engineers can design processes that operate continuously rather than intermittently. Production lines, chemical plants, and mining operations can be run with minimal downtime. Solar energy allows machines to function autonomously for extended periods, reducing the need for constant human intervention. The combination of reliable power and proximity to valuable resources forms a foundation for industrial and economic growth on the moon. The efficiency and simplicity of lunar solar power provide an advantage over Earth based energy systems. On Earth, power generation must contend with atmospheric conditions, weather, and infrastructure limitations. On the moon, the direct sunlight, lack of clouds, and minimal interference from particles in the air improve energy efficiency. Energy can be deployed where it is needed most, directly to industrial sites, without the complexity of a large transmission grid. This efficiency contributes to the overall feasibility of lunar operations and the potential for large-scale economic development. Future lunar industrial plans rely heavily on the ability to generate and manage solar energy. By combining knowledge of sunlight patterns, terrain, and technology, operations can produce continuous power for mining, chemical processing, and habitat support. Solar energy systems are integrated with resource mapping, extraction planning, and transportation strategies, forming a complete network that enables self-sufficient operations. The moon's natural conditions allow energy systems to function effectively, supporting economic activity that would be more difficult and costly on Earth. By leveraging high-intensity sunlight, near continuous illumination, and predictable cycles, solar power becomes the backbone of lunar industry. Panels can be placed on peaks of eternal light, linked to storage or processing facilities in nearby craters, and used to power machinery and chemical systems. The combination of resource accessibility, efficient energy collection, and autonomous technology positions the moon as a location where industrial activity can be sustained with minimal reliance on Earth. Energy from the sun thus forms a crucial component of the moon's economic potential and underpins the possibility of large-scale operations that produce materials, fuel, and products for use in space or on Earth. Establishing infrastructure on the moon requires careful planning due to the unique environmental conditions. Lunar bases must provide protection from radiation, extreme temperatures, and micrometeorite impacts while supporting industrial and human activity. Landing pads are among the first structures to be constructed, designed to stabilize spacecraft during arrival and prevent the dispersal of regolith caused by rocket exhaust. The choice of material and design is informed by studies of soil mechanics, the abrasive nature of lunar dust, and the need to withstand repeated landings. Reinforced pads can be built from compacted regolith, concrete made from lunar soil, or prefabricated modules transported from Earth. Habitat modules are designed to support life in low gravity, low pressure, and high radiation environments. Pressure vessels maintain breathable air and provide thermal regulation. Interiors are insulated to reduce energy loss and maintain stable temperatures. Designs often incorporate modular components, allowing habitats to expand as additional crews arrive or industrial operations grow. These modules can be linked together through pressurized tunnels or airlocks, enabling movement between living areas, laboratories, and workspaces without exposure to the outside environment. Construction on the moon increasingly relies on local materials to reduce the need for supplies from Earth. Lunar regolith can be compacted or sintered into solid blocks for walls, landing pads, or protective barriers. Regolith's natural properties, including its density and mineral composition, make it suitable for radiation shielding. By covering habitats or critical infrastructure with meters of regolith, exposure to cosmic rays and solar particle events is greatly reduced. Techniques for using regolith include molding it into bricks, creating layered walls, or 3D printing structures directly on site using robotic systems. Additive manufacturing, or 3D printing, offers a practical solution for building complex structures on the moon. Machines can layer regolith mixed with binding agents to form walls, domes, or support beams. These structures can be created with precise dimensions and customized designs to suit operational needs. The process minimizes human labor while maximizing the use of local materials. By employing autonomous systems, construction can proceed continuously, even in locations where human presence is limited or intermittent. Robotics and autonomous machinery are essential for building and maintaining lunar infrastructure. Excavators, transporters, and assembly robots can operate in low gravity and extreme temperatures. Sensors, cameras, and AI guided systems allow these machines to navigate uneven terrain, handle delicate materials, and perform repetitive tasks efficiently. Robotics can also prepare sites for construction, including leveling surfaces, compacting regolith, or arranging modular components. By reducing reliance on human labor, operations become safer, faster, and more scalable. Landing pads must also account for the mechanical effects of rocket exhaust on the surface. Lunar soil is fine and abrasive, and high-velocity exhaust can blast particles outward, potentially damaging nearby equipment or habitats. Solutions include reinforced surfaces, regolith berms, or layered mats that absorb energy. Some designs incorporate modular, transportable pads that can be repositioned as operations expand. Properly engineered landing zones are essential for the safety of both spacecraft and crew. Storage facilities and industrial structures are also constructed using local materials when possible. Regolith provides insulation against temperature extremes and shielding from radiation. Combined with structural supports or frameworks, regolith-based buildings can protect sensitive equipment, fuel depots, and life support systems. Covering facilities with regolith reduces thermal fluctuations and helps maintain stable internal conditions, which is critical for machinery that relies on precise temperatures. Habitat and industrial designs consider the moon's gravity, which is 1/6 that of Earth. Structural loads are lower, allowing lighter frameworks and simpler support systems. However, low gravity also affects fluid behavior, material handling, and mechanical operations. Construction methods must adapt to these differences, ensuring that walls, supports, and equipment remain stable and functional. Robotics, in combination with modular and additive techniques, provides a flexible solution that can adjust to changing site requirements. Additive manufacturing also allows creation of specialized shielding and structural forms. Domed habitats or protective enclosures can be built directly on site without requiring prefabricated components. This approach reduces transportation costs from Earth and allows for customization based on local terrain and resource availability. Regolith-based concrete or sintered soil can be used to reinforce critical points, absorb impacts, and provide thermal stability. The resulting structures are integrated into the natural landscape, minimizing environmental disruption and maximizing efficiency. Water, ice, and volatiles harvested nearby influence habitat placement and infrastructure planning. Facilities can be sited close to extraction points to reduce transportation requirements. Energy from solar arrays can be routed directly to habitats and industrial machinery. The combination of local resources, energy availability, and autonomous systems forms a cohesive network in which extraction, processing, and storage can operate in parallel. Infrastructure planning must account for both current operations and future expansion, ensuring scalability and sustainability. Communication infrastructure is also critical. Lunar bases rely on satellite relays, line of sight antennas, and relay stations to maintain contact with Earth and orbital assets. Antennas and relay towers must be placed strategically to avoid interference from terrain features. Autonomous systems can deploy and maintain these networks, ensuring continuous communication for both industrial operations and human activities. Reliable communications are essential for control of remote machinery, monitoring of habitats, and coordination of resource transport. Thermal management is an important consideration for infrastructure. Habitats and machinery must be insulated against both extreme heat and extreme cold. Regolith provides natural insulation, but additional measures include reflective coatings, internal heating, and radiative cooling systems. Solar energy can supply heat and power simultaneously, allowing energy intensive operations to function continuously. Placement of equipment and habitats takes into account solar exposure, shadow patterns, and terrain orientation to optimize temperature control. Maintenance of lunar infrastructure relies heavily on robotics and autonomous systems. Machines equipped with sensors and repair tools can monitor structural integrity, clear regolith from surfaces, and perform routine inspections. Remote controlled systems provide backup support where human presence is limited. By combining autonomous maintenance with modular construction, infrastructure can adapt to changing operational needs and recover from minor damage without requiring continuous human labor. Additive manufacturing also allows for rapid replacement of worn or damaged components. Spare parts can be produced on site using local materials, reducing dependence on Earth based supply chains. This capability supports continuous operation of industrial processes, life support systems, and structural repairs. By integrating manufacturing, construction, and maintenance, lunar bases can achieve high levels of self sufficiency. Landing pads, roadways, and transport corridors are critical components of infrastructure. Well constructed pads reduce dust disruption during landings, while stabilized paths allow vehicles and machinery to move efficiently across the surface. Compacted regolith, sintered soil, or prefabricated modular surfaces can provide durable routes. These pathways also support energy distribution lines, communications, and access to resource extraction sites. Proper planning of transport infrastructure ensures operational efficiency and safety. Long-term planning of lunar infrastructure considers expansion as operations grow. Habitats can be extended, industrial facilities scaled, and energy systems upgraded. Autonomous machinery can construct new modules or repurpose existing structures. This approach allows industrial activity to evolve over time, maintaining flexibility while supporting increasing output. By using local materials, renewable energy, and robotic construction, lunar infrastructure can expand without excessive reliance on Earth. The integration of habitats, industrial structures, energy systems, and communication networks creates a functional and sustainable lunar environment. Regolith based construction, additive manufacturing, and autonomous operations reduce dependence on Earth, while careful planning of placement, orientation, and protective measures ensures efficiency and safety. Each component, from landing pad to habitat, contributes to a cohesive network that enables continuous industrial and scientific activity on the lunar surface. In summary, infrastructure development on the Moon relies on modular habitats, landing pads, and energy systems, and industrial facilities. Regolith serves as a versatile building material for walls, shielding, and roadways. Additive manufacturing and autonomous machinery allow construction and maintenance with minimal human labor. Strategic placement near resources, solar energy, and transport corridors maximizes efficiency. Together, these elements form the foundation for sustained human and industrial presence on the Moon, enabling operations that can support economic growth, resource extraction, and long-term habitation. Mining operations on the Moon are centered on extracting valuable metals, helium-3, and other rare elements from the surface and shallow subsurface. Regolith contains concentrations of titanium, aluminum, iron, and small amounts of rare earth elements. These metals are distributed in varying densities, with some basins offering higher concentrations than others. Extraction begins with robotic excavation of regolith, using machinery adapted to low gravity and abrasive soil. Excavators dig, scoop, or drill into the surface to collect material, which is then transported to processing facilities. Conveyor systems, robotic carriers, or hopper vehicles move regolith efficiently, reducing human labor and exposure to environmental hazards. Helium-3, a rare isotope implanted by the solar wind over billions of years, exists in trace amounts within lunar soil. The extraction of helium-3 requires heating regolith to high temperatures, typically above 600 degrees Celsius, to release the gas. The vaporized helium-3 is collected, cooled, and stored in cryogenic tanks for later use in nuclear fusion or other energy applications. This process demands precise temperature control, energy input, and careful handling to maximize yield while minimizing losses. The combination of automated excavation, controlled heating, and storage systems allows continuous recovery of helium-3 in quantities sufficient to support industrial needs over time. Or refinement on the moon uses both physical and chemical processes. Metals in regolith are often bound within oxides or mixed with silicate minerals. Techniques such as magnetic separation, electrostatic sorting, and high temperature reduction allow metals to be isolated from the surrounding material. In low gravity, handling of particles is different from Earth. Fine dust tends to float or cling to surfaces due to electrostatic forces, requiring containment and careful transport. Machinery is designed to operate in vacuum, prevent dust contamination, and maintain precise control over particle flow. These adaptations ensure that refined materials meet required standards for industrial use. Titanium-rich areas, particularly in Maria regions, provide a source of ilmenite, which contains both titanium and iron. Ilmenite can be processed to extract oxygen for fuel or life support, in addition to the metals themselves. Electrochemical reduction of ilmenite produces usable oxygen gas and metal residues suitable for construction or manufacturing. Aluminum extraction from anorthosite-rich highlands follows a similar approach, using high temperature reduction to isolate the metal from its oxide form. By using these techniques, industrial operations can produce both raw metals and vital resources, such as oxygen for further applications. Industrial scaling is a primary consideration for lunar operations. Small-scale extraction can supply experimental facilities or short-term projects, but large-scale operations require coordination of excavation, transport, refinement, and storage. Modular systems allow multiple machines to operate simultaneously, each performing a specific task within the processing chain. Robotic arms, conveyor belts, and heating units work in unison to maintain continuous flow of materials. Scaling also requires careful planning of energy supply, waste management, and maintenance of machinery to prevent disruptions in production. Processing rare earth elements and trace metals presents additional challenges. These elements exist in small concentrations and are often dispersed throughout the regolith. Chemical separation techniques, including selective leaching, flotation, and electrochemical methods, are used to isolate valuable compounds. Machinery is designed to handle low-gravity conditions, ensuring proper mixing, separation, and collection of target elements. Control systems monitor chemical reactions, particle movement, and product quality to ensure consistent results. These processes are slower than bulk metal extraction, but are necessary for high-value industrial products. Transportation of mined material between excavation sites and processing facilities is optimized for efficiency. Low gravity allows vehicles to carry larger loads relative to their weight, but soil friction, slopes, and abrasive regolith create mechanical challenges. Wheeled rovers, tracked vehicles, or hopper systems are adapted to navigate uneven terrain, maintain traction, and prevent dust interference. Routes are planned to minimize energy use and wear on machinery while maintaining continuous supply of material to refinement centers. Storage bins and intermediate transfer stations provide buffer capacity, enabling operations to continue without interruption. Automation is critical to mining operations. Excavation, transport, and processing can be coordinated by central control systems, which monitor the performance of each component and adjust operations as needed. Autonomous systems reduce the need for constant human supervision and allow mining to proceed continuously, including during periods when human crews are unavailable. Sensors, cameras, and AI guided software provide real time feedback, ensuring that machinery operates efficiently and safely in the lunar environment. Helium 3 extraction requires integration with thermal systems and energy management. Heating regolith to release helium 3 consumes large amounts of energy, which can be supplied by nearby solar arrays. The process must maintain stable temperatures across large volumes of soil to ensure efficient gas release. Cooling and collection systems then capture helium 3 and separate it from other volatiles. This operation benefits from proximity to energy sources, robotic support, and storage infrastructure, allowing continuous extraction and accumulation of this valuable isotope. Metals and other refined materials are stored or transported to industrial sites for further use. Titanium, aluminum, iron, and other metals can be formed into structural components, support frames, or manufacturing feedstock. Oxygen recovered from ilmenite or water ice can be used for chemical reactions, fuel production, or life support systems. The combination of raw materials and processed products supports a complete industrial ecosystem on the moon, enabling continuous operation without reliance on Earth-based supply chains. The abrasive nature of regolith affects machinery design and operational efficiency. Moving parts, bearings, and surfaces must be resistant to wear caused by dust particles. Sealed systems, dust shields, and controlled enclosures are used to protect sensitive equipment. Lubrication, cooling, and periodic maintenance are planned to ensure long-term functionality. By addressing these challenges, mining operations can maintain continuous output with minimal downtime. Low gravity conditions influence both material handling and chemical processing. Particles behave differently than on Earth, often floating or adhering to surfaces due to electrostatic forces. Machinery is designed to contain, transport, and process these particles efficiently using specialized conveyors, hoppers, and separators. Mixing and chemical reactions must account for reduced convective flow, requiring agitation or alternative methods to achieve uniform results. These adaptations are essential for maintaining the quality and consistency of refined products. The potential for production scaling depends on the integration of excavation, processing, energy supply, and storage. Large-scale mining operations can produce thousands of tons of regolith per year, providing metals, volatiles, and rare elements for industrial and scientific use. Expansion is achieved by deploying additional robotic systems, increasing energy capacity, and establishing new processing modules. By connecting resource extraction with energy generation and storage infrastructure, lunar operations can grow in both size and complexity while maintaining efficiency. Challenges remain in maintaining high temperature processing, managing volatiles, and preventing contamination. Helium 3, hydrogen, and other gases must be handled in vacuum or low pressure conditions with cryogenic storage to prevent loss. Dust control is critical to prevent interference with both machinery and chemical reactions. Ongoing monitoring, remote control, and autonomous adjustment ensure that production continues safely and effectively. These measures are integrated into the overall industrial system, allowing consistent output over long periods. By combining excavation, processing, and storage, lunar mining supports multiple industrial applications. Metals provide construction materials for habitats, machinery, and energy systems. Helium 3 offers a potential fuel source for fusion energy. Rare elements supply critical materials for electronics and advanced technologies. Oxygen and other volatiles support chemical processes and life support. Each component is interlinked, creating a self-sustaining industrial network that maximizes efficiency and reduces dependence on Earth. Resource mapping guides the placement of mining operations. Areas with high concentrations of titanium, aluminum, or helium 3 are prioritized to maximize yield. Orbital observations, spectral analysis, and in situ sampling provide detailed information on composition, depth, and accessibility. By coordinating site selection with energy supply, storage facilities, and transport corridors, industrial operations can maintain continuous production and expand strategically. Long-term operations integrate mining with habitat support, energy systems, and manufacturing. Excavated materials are used both as raw products and construction resources. Energy from solar arrays powers chemical reactions, heating systems, and machinery. Autonomous systems handle excavation, transport, and processing. By linking these elements, lunar industrial activity becomes self-sufficient, scalable, and capable of continuous operation, laying the foundation for a productive and sustainable presence on the Moon. Transportation between the Moon and Earth relies on careful calculations of orbital mechanics and energy requirements. The delta V, or change in velocity, needed to move from the lunar surface to low lunar orbit is approximately 1.6 kilometers per second. From there, a spacecraft must achieve an additional delta V of roughly 0.9 kilometers per second to enter a trans-Earth trajectory. These energy requirements are significantly lower than launching directly from Earth to low Earth orbit, which requires about 9.4 kilometers per second. By using the Moon as a staging area, industrial operations can reduce the total fuel needed for transport, making space-based logistics more efficient. Reusable lunar landers play a central role in this system. These vehicles are designed to shuttle between the lunar surface and orbital stations multiple times without full refurbishment. Fuel, power systems, and thermal protection are optimized for repeated use. By landing on the Moon, delivering cargo, and returning to orbit, these landers support the continuous movement of raw materials, refined products, and industrial equipment. Reusability reduces the need to launch new vehicles from Earth for each operation, lowering both cost and launch frequency. Orbital transfer stations serve as hubs for cargo and fuel management. Located in low lunar orbit or at stable libration points, these stations provide refueling, storage, and processing capabilities. Materials lifted from the surface can be stored temporarily, repackaged, or combined with propellant before transfer to Earth or other destinations in space. These stations also allow spacecraft to operate more flexibly, timing departures to match optimal trajectories, minimizing fuel consumption, and ensuring predictable delivery schedules. Fuel production on the Moon supports transportation efficiency. Hydrogen and oxygen extracted from water ice or other volatiles can be converted into rocket propellant. By producing fuel in situ, spacecraft can refuel on the Moon instead of carrying all propellant from Earth. This reduces the total mass that must be launched from Earth and increases the payload capacity for materials or industrial products. The combination of local fuel production and reusable landers creates a self-sustaining transportation loop that supports continuous operations. Logistics planning involves scheduling launches, transfers, and landings to minimize downtime. Delta V calculations guide the selection of transfer windows, ensuring that spacecraft use the least energy for each movement. Orbital mechanics also influence timing, as the moon's position relative to Earth affects trajectory and travel duration. By carefully coordinating these factors, transportation systems can operate efficiently, moving materials between the lunar surface, orbital stations, and Earth with minimal energy expenditure. Payload optimization is a critical aspect of lunar transport. Cargo is arranged to balance mass distribution, protect sensitive equipment, and maximize the amount of material delivered per trip. Containers are designed to withstand vacuum, temperature fluctuations, and mechanical stress during landing and takeoff. Efficient packing and handling. Systems reduce wasted space and weight, increasing overall throughput. Each launch is therefore planned to deliver the greatest possible benefit in terms of mass, value, and operational efficiency. Cost advantages arise from in-space resource utilization. Materials mined and refined on the moon can be transported to Earth orbit or beyond without launching them from Earth. This reduces dependence on terrestrial launches, which are expensive and energy intensive. Metals, helium-3, and other industrial products become economically viable when transported from the moon using reusable spacecraft and orbital infrastructure. Over time, these advantages accumulate, enabling profitable space-based industries and reducing the financial burden of repeated Earth launches. Supply chains on the moon integrate surface operations with orbital transfer and Earth delivery. Excavation, processing, and storage facilities are located near energy and resource sources. Materials are transported to orbital stations via landers or automated cargo vehicles. From orbit, spacecraft carry products to Earth, other orbital stations, or destinations elsewhere in the solar system. Each stage is coordinated to maintain continuous flow, minimizing idle time and maximizing output. Logistics systems are designed for reliability, predictability, and adaptability to changing conditions. Industrial operations benefit from modular transport solutions. Small reusable landers can carry concentrated payloads, while larger vehicles move bulk materials. Containers and modules are standardized to allow interchange between different vehicles and orbital stations. Automation in docking, loading, and unloading reduces human labor and the risk of errors. Robotic systems can manage the majority of cargo handling, maintaining high throughput and efficiency. Standardization and automation together support scalable, continuous industrial operations. Orbital mechanics also dictate launch trajectories, from the moon to Earth or other destinations. The moon's low gravity allows for multiple options in transfer paths, including free return trajectories, direct insertion into low Earth orbit, or delivery to geostationary or interplanetary trajectories. Each path is selected based on energy efficiency, timing, and payload requirements. Proper trajectory planning ensures that launches occur with minimal fuel use and maximum safety for cargo and spacecraft. Energy considerations influence all transport operations. Propellant requirements depend on delta V, vehicle mass, and efficiency of engines. By producing fuel on the moon, energy use is shifted away from Earth-based launches, concentrating power production locally. Solar arrays, reactors, or other energy sources on the lunar surface supply the necessary electricity for extraction, electrolysis, and processing of fuel. Integration of energy production with transport logistics creates a coordinated system where materials, fuel, and energy flow efficiently through the network. Reusable spacecraft reduce risk by allowing testing, maintenance, and incremental improvement. Each vehicle can be upgraded or repaired at orbital stations, extending operational life. Components can be replaced or refitted without launching new vehicles, thus reducing cost and increasing reliability. Maintenance procedures include inspections, component swaps, and system recalibration. The ability to reuse vehicles over multiple missions creates a sustainable cycle of transport and logistics, critical for large-scale industrial operations on the moon. Economic modeling of lunar transport highlights the importance of reducing launch mass from Earth. Every kilogram lifted from the moon requires significantly less energy than the same mass from Earth. When combined with local resource production, reusable landers, and orbital transfer infrastructure, the cost per kilogram of transport material decreases substantially. These factors make in space industries more feasible and economically competitive compared with Earth launched equivalents. Transport schedules are aligned with operational demand. Mining operations, fuel production, and industrial processing must coordinate with lander availability, orbital transfer windows, and Earth delivery dates. Buffer storage at the surface and in orbit ensures that supply continues during temporary disruptions or delays. By integrating timing, energy use, and operational capacity, lunar supply chains maintain efficiency and continuity over long periods. Advanced automation supports navigation, docking, and cargo transfer in orbit. Spacecraft are equipped with sensors, cameras, and AI assisted control systems to manage complex maneuvers. Docking with orbital stations, or rendezvous with other vehicles, is conducted with precision, minimizing fuel expenditure and mechanical stress. Automation reduces the need for continuous human control and allows multiple transport cycles to occur simultaneously. This capability is critical for high throughput industrial operations that rely on frequent and predictable transfers. Lunar to Earth transportation also considers environmental factors. Vehicles must survive temperature extremes, radiation exposure, and micrometeoroid impacts. Thermal shielding, radiation hardened electronics, and protective structures ensure reliable operation during transit. Cargo modules are insulated and reinforced to protect materials, especially volatile compounds or delicate industrial products. Proper design and planning allow safe and efficient transport from the lunar surface to orbital stations and onward to Earth or other locations in space. Integration of energy, logistics, and industrial production forms a complete system. Solar energy on the moon powers excavation, processing, and fuel production. Reusable landers shuttle materials to orbital stations. Orbital stations provide refueling, storage, and transfer services. And spacecraft deliver products to Earth or other destinations. This interconnected network allows continuous operation, maximizes efficiency, and enables the moon to function as a hub for industrial activity and economic growth in space. Over time, transport systems scale with industrial output. Increased production requires additional landers, expanded orbital facilities, and optimized supply routes. Automation, standardization, and modular design allow incremental growth without disrupting existing operations. By linking energy, resources, and transport in a coordinated network, the moon becomes capable of supporting sustained industrial activity with predictable costs and continuous delivery of materials to Earth or space-based destinations. By leveraging reusable vehicles, in situ fuel production, orbital transfer infrastructure, and precise orbital mechanics, lunar transport and supply chains achieve efficiency and sustainability. This framework supports industrial scaling, resource exploitation, and economic development, providing a foundation for a self-sufficient lunar presence. The combination of low-gravity launches, predictable delta-V requirements, and coordinated logistics makes the moon a practical platform for continuous industrial operations and transport to Earth and beyond. The moon provides a platform for scientific research across multiple disciplines. Its surface hosts laboratories where materials science experiments can take place in low gravity. Reduced gravitational forces affect the behavior of liquids, powders, and crystalline structures, enabling studies that are difficult or impossible on Earth. Experiments can analyze how metals and alloys form, how composites respond to stress, and how particle interactions differ in vacuum and low gravity. These studies inform the development of advanced materials for industrial, construction, and aerospace applications. Astrophysics research benefits from the moon's stable surface and lack of atmosphere. Telescopes positioned on the lunar surface can observe the universe without distortion caused by atmospheric turbulence. The far side of the moon, permanently shielded from Earth based radio signals, offers an ideal location for radio astronomy. Observatories there can detect faint cosmic signals, study the formation of stars and galaxies, and investigate the early universe. Minimal interference and stable environmental conditions make the moon a unique site for sensitive instruments. Biological studies are conducted in controlled habitats where plants, microorganisms, and small animals can be studied under low gravity and reduced pressure. These experiments provide insight into life support systems, adaptation to extraterrestrial environments, and the long term effects of partial gravity on biological processes. Understanding how organisms respond to the moon's environment helps plan for future space missions and deep space colonization. Controlled experiments also inform habitat design, nutritional systems, and waste recycling techniques. The moon serves as a testing ground for technologies essential to human presence as beyond Earth. Life support systems, water recycling units, and energy management solutions can be trialed in realistic conditions. Habitats and industrial modules provide a controlled environment where new machinery, robotics, and automation techniques can be evaluated. Testing on the moon identifies potential failure modes, informs improvements, and validates performance under extended operational conditions. By solving technical challenges on the moon, engineers can reduce risk for missions to Mars and deeper space. Industrial methods can be refined in the lunar environment. Mining equipment, processing systems, and additive manufacturing techniques can be operated on a small or moderate scale to evaluate efficiency, durability, and scalability. Materials extracted from the moon provide input for these experiments, linking resource utilization with technology testing. Techniques that succeed on the moon can later be adapted for more distant locations, where in situ resource use will be critical. Energy systems are trialed in the lunar environment. Solar arrays, energy storage, and power management solutions are tested in real world conditions, including the long lunar day night cycle and extreme temperatures. Continuous operation and integration with industrial processes provide data on efficiency, reliability, and maintenance requirements. Lessons learned from energy management on the moon inform the design of systems for larger colonies and interplanetary operations. Robotic systems are a focus of technological testing. Excavators, transporters, construction robots, and autonomous machinery are deployed on the moon to operate under low gravity and abrasive soil conditions. Performance data from these operations guide improvements in design control algorithms and durability. Long duration deployment allows engineers to study wear, fatigue, and system resilience, providing insight into machinery for future deep space applications. The lunar environment also supports experimentation with remote operations. Human supervisors can control robotic systems from orbit or Earth, testing latency effects, automation protocols, and fail-safe procedures. These experiments refine methods for managing industrial and scientific activity at a distance, which is essential for operations in Mars orbit or other remote locations. Understanding the interaction between humans and autonomous systems in low gravity informs future mission planning. Materials processing in low gravity provides unique opportunities. Chemical reactions, fluid dynamics, and phase changes behave differently under the moon's gravity. Controlled experiments can observe sedimentation rates, crystal growth, and particle separation without the influence of strong gravitational forces. These insights contribute to the development of more efficient manufacturing processes for aerospace, energy, and industrial applications. The moon's vacuum environment allows testing of processes that are sensitive to pressure or atmospheric composition. High vacuum manufacturing, coating techniques, and chemical reactions can be performed without interference from air or humidity. Materials produced in these conditions may have unique properties not achievable on Earth. Combining vacuum conditions with low gravity creates a laboratory environment distinct from any terrestrial facility, suitable for high precision experimentation. Lunar laboratories provide long term monitoring of environmental effects, and sensors can measure cosmic radiation, solar particle flux, micrometeoroid impacts, and temperature cycles. Continuous data collection informs habitat design, material selection, and industrial planning. These observations support both scientific research and the development of technologies intended for sustained operation in space. Astrophysical instruments can utilize the moon's stable thermal environment. Unlike Earth, where atmospheric and diurnal variations affect sensitive equipment, the lunar surface provides consistent temperatures and minimal vibration. Instruments can operate with reduced cooling requirements and increased observation stability. This allows for high resolution imaging, precise spectral analysis, and extended duration monitoring of celestial objects. Resource testing is an integral part of technological development. Extraction, processing, and material handling systems are operated on site to validate methods for future scaling. For example, testing metal extraction, helium-3 recovery, and regolith processing under lunar conditions provides practical data for industrial planning. Insights gained from these tests reduce uncertainty, improve efficiency, and confirm the feasibility of lunar-based production methods. The moon also serves as a proving ground for long-duration human habitation technologies. Habitat modules, life support systems, and energy networks are tested in a partially isolated environment. This allows evaluation of redundancy, system resilience, and integration of multiple subsystems. Lessons learned contribute to the design of more reliable and sustainable habitats for extended missions, both on the moon and on distant planets. Communication systems are tested under realistic lunar conditions. Long distance radio transmissions, satellite relays, and networked control systems are evaluated for latency, reliability, and redundancy. These tests are critical for coordinating industrial operations, scientific experiments, and human presence in remote locations. Performance data informs improvements in hardware, software, and operational protocols. Environmental monitoring provides insight into dust behavior, regolith stability, and surface interaction with structures. Understanding how lunar soil responds to excavation, vibration, and human or robotic activity helps design foundations, protective barriers, and machinery. Continuous observation ensures that construction, transportation, and industrial systems remain effective and safe. The combination of scientific research, technology testing, and industrial validation positions the moon as a strategic location for human advancement in space. By integrating laboratories, manufacturing, energy systems, and robotic operations, the lunar environment functions as a living testbed. Innovations developed here can later be applied to Mars, asteroid missions, and deep space exploration with reduced risk and validated performance. Long-term projects focus on developing methods that will enable large-scale industrial and scientific activity. Testing in situ allows for iterative improvement, where each experiment informs the next. This cycle supports continuous innovation while reducing dependence on Earth-based trials. The moon thus becomes a bridge between experimental research and operational deployment, providing both data and practical experience for future space ventures. In addition to scientific and industrial applications, the moon allows testing of operational integration. Energy systems, transport networks, habitats, and processing facilities can be operated simultaneously. This integrated approach provides insight into coordination, maintenance, and scalability. Engineers can refine scheduling, automate workflows, and optimize resource allocation based on practical experience in a controlled but realistic extraterrestrial setting. Ultimately, the moon functions as a proving ground for technologies essential to sustained human and industrial presence in space. Laboratories test materials, instruments, and biological systems. Industrial methods are validated under low gravity and vacuum conditions. Energy, transport, and infrastructure systems are integrated and refined. By observing, measuring, and iterating on these processes, scientists and engineers gain critical knowledge that informs deeper space exploration and industrial expansion, establishing the moon as a center for innovation and technological advancement. The moon's resources have the potential to generate economic value that surpasses many Earth based industries. Metals such as titanium, aluminum, and iron, combined with rare earth elements and helium 3, form a portfolio of commodities with high demand for advanced technology, energy, and construction applications. The scarcity of helium 3 on Earth, in particular, gives it potential for significant economic impact if fusion technology becomes viable. By extracting these materials from the lunar surface and processing them in situ, a supply of high value resources can be maintained continuously, supporting industrial expansion both in space and on Earth. Economic models consider the costs of establishing infrastructure, energy, generation, and transport against the potential value of extracted resources. Lunar operations benefit from low gravity, which reduces fuel consumption for launching products to orbit or Earth. In-space processing minimizes transport mass by refining materials near the extraction site. When integrated with reusable landers, orbital transfer stations, and autonomous mining, the overall cost per kilogram of high-value products can be lower than equivalent terrestrial operations that require extensive labor, energy, and environmental management. Metals extracted from the moon have industrial applications on Earth and in space. Titanium and aluminum can be used in aerospace, construction, and energy infrastructure. Iron supports manufacturing and alloy production. Rare earth elements are critical for electronics, magnets, and renewable energy technologies. Each of these markets is growing on Earth, making lunar mining economically relevant. By tapping into these high demand commodities, lunar enterprises can capture value that would be difficult to match with terrestrial mining alone. Helium 3 presents a unique opportunity for energy markets. If nuclear fusion reactors capable of using helium 3 are developed, the isotope's scarcity on Earth gives lunar extraction enormous potential value. A steady supply of helium 3 from lunar regolith could support a new class of energy production with minimal greenhouse gas emissions and high energy density. This potential creates economic incentives for nations and private companies to invest in lunar resource acquisition, as the payoff could exceed the costs of transport, processing, and infrastructure over time. Comparisons to terrestrial mining illustrate the efficiency of lunar operations. Earth-based mining requires extensive excavation, water management, labor, and environmental remediation. By contrast, the moon's vacuum and low gravity simplify extraction and transport processes, reducing operational complexity. Solar energy provides continuous power near the poles, eliminating the need for fossil fuels or complex energy grids. While initial investment is high, long-term operation can yield a net gain as industrial throughput increases and transport costs decline. Resource-rich regions on the moon are mapped using satellite spectroscopy, orbital imaging, and in situ sampling. This data informs site selection for mining and industrial development. Targeting high concentration deposits of metals, helium 3, or volatiles improves efficiency, maximizing output while reducing operational risk. By strategically placing extraction and processing facilities near these deposits, companies can increase profitability and maintain continuous production without excessive energy expenditure. Industrial scaling affects economic potential. Modular processing facilities, automated mining machinery, and integrated transport networks allow operations to grow incrementally. Additional landers, orbital stations, and energy infrastructure can be deployed as production expands. By scaling efficiently, lunar industries can meet global demand for metals, rare elements, and energy products. Each increment of production reduces per unit costs, increasing profitability and economic return over time. Companies and nations are increasingly focused on lunar resource acquisition. International space agencies have begun planning missions for prospecting, mining, and infrastructure development. Private enterprises are investing in robotics, landers, and orbital facilities capable of transporting material between the Moon and Earth orbit. Collaborative and competitive efforts drive technological innovation, optimize operational efficiency, and lay the groundwork for economically sustainable lunar industries. Investment models consider the value of extracted materials against operational and development costs, mining, refining, energy production, and transport. Infrastructure represents significant capital outlays. Long term projections account for industrial growth, technological improvements, and resource scarcity. The combination of high value resources, reduced transport energy, and the potential for in space manufacturing increases the overall economic viability. Over decades, a sustained lunar production could generate wealth exceeding many traditional Earth based industries. Market potential extends beyond immediate commodity sales. Metals and rare elements can support in space construction for orbital stations, spacecraft, and industrial modules. Energy generated from helium 3, if fusion reactors are developed, could supply power to orbital platforms or terrestrial fusion plants. The Moon therefore functions both as a source of raw materials and as a platform for broader industrial expansion in space, enhancing the overall economic potential of lunar development. Economic projections emphasize risk management and efficiency. Although Schu's initial investment in infrastructure, transport, and machinery is substantial, but low gravity extraction, local resource utilization, and solar energy reduce ongoing operational costs. Reusable landers and autonomous systems further decrease expenses, allowing for sustainable, long term production. As industrial networks mature, economies of scale emerge, increasing profitability and reinforcing the economic case for lunar investment. Supply chains are designed to maximize resource value. Excavated materials are refined on site, transported to orbital stations for storage, and then delivered to Earth or other industrial nodes. Efficient integration of mining, processing, and transport ensures continuous flow, minimizing idle time and maximizing revenue potential. Automation and robotics support consistent output, reliability, and cost control, which are essential for high value commodities in competitive global markets. Comparative analysis shows that lunar industrial operations can outperform terrestrial counterparts in specific sectors. The low gravity, abundant solar energy, and concentration of certain rare elements allow processes to occur more efficiently and with less environmental impact. Terrestrial mining faces water scarcity, regulatory limitations, labor costs, and energy constraints, whereas the Moon provides a clean and predictable environment for continuous industrial activity. These advantages create opportunities for companies and investors willing to engage in space based resource development. Emerging companies focus on automation, robotics, and reusable transport solutions. By developing modular mining systems, orbital transfer stations, and processing facilities, private enterprises can scale production to meet demand. Early investment in infrastructure and technology positions these companies to capture high value resources and establish market leadership. Nations supporting such initiatives benefit from access to strategic materials, energy potential, and technological advancement. Helium 3 extraction represents a high risk, high reward opportunity. The isotope is rare on Earth, and lunar regolith contains measurable quantities accumulated over billions of years. Successful extraction and storage could provide a fuel source for future fusion reactors, offering energy with high efficiency and minimal environmental impact. Investors and industrial planners consider this long term potential when designing economic models for lunar resource acquisition. Integration of energy, materials, and transport forms the basis for sustained economic growth. Mining operations supply metals and helium 3. Processing facilities refine resources, and reusable landers deliver products to orbital stations or Earth. Solar energy powers extraction and processing systems. Robotics and automation maintain continuous production. By linking these elements in a coordinated network, industrial activity on the moon can achieve profitability and long term sustainability. The potential for billionaires to emerge from lunar industries is linked to early investment and strategic advantage. Companies or nations that establish infrastructure, resource access, and transport networks first can capture market share, control supply chains, and benefit from increasing demand. The high value of helium 3, rare metals, and industrial feedstock positions lunar resource operators as potential leaders in a new class of space based wealth generation. Economic modeling predicts that lunar industrial activity can eventually exceed the output of many Earth based sectors. Metals, rare elements, and helium 3 provide multiple revenue streams. In space manufacturing, orbital construction, and energy production further increase economic output. By leveraging low gravity advantages, solar energy, reusable transport, and autonomous systems, the moon can support industries that generate significant wealth, creating conditions for billionaires to emerge from space based operations. Ultimately, the moon's combination of high value resources, efficient industrial processes, and scalable transport infrastructure provides a foundation for sustained economic activity. Mining, processing, and transport networks enable continuous operation. Energy and resource utilization reduce costs and increase profitability. Early movers in this environment have the potential to establish significant financial advantage, demonstrating the economic feasibility of lunar industries and the possibility of wealth exceeding that available from traditional Earth based operations. The moon's role as a platform for future space expansion extends beyond its surface. Lunar bases can function as staging areas for missions to Mars, asteroids, and deeper regions of the solar system. By producing fuel from water ice, oxygen, and other volatiles, lunar facilities reduce the amount of material that must be launched from Earth. This lowers energy requirements, cost, and risk for long distance missions. Refueling depots and orbital stations near the moon allow spacecraft to assemble, load supplies, and depart efficiently for interplanetary destinations. Long-term industrialization of the moon supports continuous growth in both resource extraction and scientific activity. Mining operations can expand into additional basins and highland regions, while processing facilities scale to match increasing production. Additive manufacturing allows construction of infrastructure on the moon using local regolith, reducing dependence on Earth-based shipments. Robotics and autonomous systems maintain excavation, transport, and industrial processes, enabling continuous operation with minimal human intervention. Energy infrastructure continues to develop alongside industrial expansion. Large solar arrays near the lunar poles provide steady power for mining, processing, and habitat operations. Excess energy can be stored for use during periods of darkness, ensuring uninterrupted industrial activity. Over time, power systems can expand to support larger facilities, orbital stations, and interplanetary launch operations. The combination of abundant solar energy and scalable industrial methods makes the moon a sustainable hub for long-term operations. Orbital infrastructure allows for efficient coordination of materials, energy, and transport. Transfer stations, fuel depots, and storage modules in low lunar orbit or at stable libration points provide intermediate steps between the surface and Earth or interplanetary space. Materials lifted from the moon can be stored temporarily, processed further, or combined with propellant to optimize delivery to Earth, Mars, or asteroid destinations. These systems improve efficiency, reduce risk, and support scalable economic and industrial activity. Lunar bases provide platforms for testing and deploying technologies needed for Mars colonization. Life support systems, habitat construction techniques, energy management, and industrial processes can be trialed in a realistic but controlled environment. Lessons learned from operations on the Moon inform planning for Mars missions, where low gravity, extreme temperatures, and limited resources will require proven solutions. The Moon thus serves as both a production center and a testing ground for human expansion deeper into the solar system. Long-term habitation supports sustained economic growth. Habitats can house industrial operators, scientists, engineers, and maintenance personnel. Life support, energy, and resource systems are integrated with mining, manufacturing, and transport operations. Controlled habitats allow human presence to be maintained over extended periods, enabling continuous supervision of industrial and scientific activity. This continuity increases productivity, reduces operational risks, and supports large-scale economic activity. The Moon's industrial expansion influences interplanetary trade. Extracted metals, helium-3, and rare elements can be delivered to Earth, orbital stations, or deep space facilities. Industrial byproducts, energy, and processed materials support construction and operations in orbit or on distant planets. These exchanges establish lunar activity as a central node in a growing network of space-based commerce, expanding economic reach and supporting wealth creation on a scale previously impossible from Earth alone. Economic projections for lunar expansion account for multiple revenue streams. Mining of metals and rare elements supplies Earth-based industries. Helium-3 extraction provides potential fuel for fusion energy. In-space manufacturing and construction generate products for orbital platforms, spacecraft, and other planetary surfaces. Each stream contributes to an integrated lunar economy that can grow over decades, creating wealth and supporting technological advancement. Technological innovation is reinforced by industrial and scientific activity. As resource extraction, manufacturing, and transport systems scale, improvements in robotics, automation, energy management, and material processing follow. Operational experience from long-term lunar activity informs design, reliability, and efficiency. Over time, incremental innovations reduce cost, increase productivity, and expand the capacity for lunar and interplanetary operations. Transport systems continue to evolve with expansion. Reusable landers, orbital transfer stations, and propellant depots enable frequent movement of materials, fuel, and equipment. Low-gravity launches reduce energy requirements, while automated scheduling and navigation systems optimize timing and efficiency. Continuous operation is supported by modular design, maintenance procedures, and redundancy in transport networks, ensuring that industrial output can scale in line with demand. Lunar expansion also strengthens the Moon's strategic role in human space activity. By combining resource extraction, manufacturing, energy production, and transport, the Moon functions as both an industrial hub and a logistical center. Its proximity to Earth, low gravity, and abundance of useful materials make it an ideal base for supporting exploration, economic growth, and scientific advancement throughout the solar system. Emerging economies on the Moon can attract investment and generate wealth. Early movers benefit from access to high-value resources, energy infrastructure, and transport networks. Companies that establish mining, processing, and distribution capabilities gain competitive advantage. Nations participating in lunar development secure strategic materials and technological expertise. Over time, these advantages accumulate, producing economic outcomes comparable to the creation of billionaires from Earth based industries, but on a space based scale. The moon's capacity to create wealth is supported by multiple factors. Abundant solar energy allows sustained industrial activity. High value metals and rare elements provide revenue streams. Helium 3 offers potential energy solutions with global demand. Low gravity and in situ resource utilization reduce operational cost. Reusable transport, orbital infrastructure, and autonomous systems increase efficiency and scalability. Together, these elements establish a foundation for long term economic growth and industrial self sufficiency. Integration with interplanetary operations extends economic influence. Lunar facilities can supply materials, fuel, and energy to Mars missions, thus asteroid mining and deep space exploration. This integration multiplies the economic potential of lunar industries by creating interconnected markets and industrial networks throughout the solar system. The moon acts as both a production center and a gateway, increasing the reach and impact of space based economic activity. Long term industrialization on the moon encourages further technological development. Machinery, robotics, energy systems, and automated processes can be refined in operational conditions. Continuous feedback from production, transport, and scientific research supports incremental improvement. These advances enhance efficiency, reduce cost, and expand the scope of lunar operations, reinforcing the moon's role as a hub for innovation and economic growth. The moon also serves as a model for sustainable extraterrestrial industrial ecosystems. Resource extraction, energy production, habitat support, and transport networks are designed to minimize waste, optimize energy use, and ensure continuity of operations. Lessons learned from the moon's integrated systems inform the design of future colonies, industrial platforms, and interplanetary supply chains, demonstrating how self sufficient operations can be maintained beyond Earth. By establishing long term infrastructure, expanding industrial capacity, and integrating transport, energy, and scientific research, the moon becomes a center for wealth creation. Its resources, combined with scalable technology and logistics, support continuous economic growth. Early investment, strategic development, and technological innovation allow nations and companies to capture value on a scale that could surpass major Earth based industries. The potential for billionaires to emerge from lunar industries is reinforced by the moon's unique combination of factors: high value materials, in situ fuel production, low gravity advantages, and scalable industrial networks create conditions for significant economic gain. Strategic early deployment, operational efficiency, and integration with interplanetary systems amplify these effects. As lunar operations expand, the economic influence of the moon grows, shaping new markets and opportunities for wealth generation. In conclusion, the moon provides a platform for sustained industrial, scientific, and economic activity. Its resources, energy, and infrastructure support mining, manufacturing, research, and in transport. Industrial operations are scalable and integrated, with autonomous systems maintaining continuous productivity. Transport networks link the surface with orbital stations and interplanetary missions, extending economic reach. Combined, these factors position the moon as a center of wealth creation, technological advancement, and human expansion beyond Earth.